Hello, and welcome to today's webcast, Tier 1 and Tier 2 Testing Best Practices, sponsored by Brigade. Today's event will be presented by Lee Kellett. Before we begin, we'd like to go over a few housekeeping items. You can enlarge the slide area by either clicking on the maximize icon at the top right of the slide area or by dragging the bottom right corner. You can also expand and reposition many of the components on your screen, so please feel free to arrange your screen for your optimal webcast viewing experience. At the bottom of the console are multiple widgets you can use. The Q&A widget can be used to submit your questions for the live Q&A session at the end of the webcast. The Help widget has a question mark icon and will address common technical issues. If you experience any technical difficulties during the webcast, please click here. If you are unable to resolve your issue, please type your issue into the Q&A widget and a member of the webcast support team will work with you to correct the problem. This presentation will be available on demand from the Lightwave homepage within 24 hours. All registrants will receive an email reminder with a link to the archive. Now, it gives me great pleasure to introduce Lee Kellett.
Hello, everyone. Welcome to today's webinar. This is Tier 1 and Tier 2 Testing Best Practices. And I actually don't have control over my slides here. So let's fix that. There we go. Sorry about that. So I'm Lee Kellett, General Manager at Brigade. I'm happy to be here today. The housekeeping issues have been taken care of. We'll be happy to answer all questions that we can get to at the end of the webinar. And if we don't get to them, we will contact you by email with an answer to your question. We'll be able to get a list of those. So we'll be happy to follow up on all questions at the end of the webinar. Just for those of you who don't know Brigade, we're a training organization. We've been training for about 30 years, only in the fiber optic space. We have a lot of classes that we hold around the world every year. We do custom development of courses for customers who want to do their own training. We have a lot of specialty courses. We do instructor-led hands-on courses, about 200 classes a year around the country and around the world. We have some online learning as well, some DVDs, which will be eventually converted to online content over the coming year. So lots of opportunity to connect with us on the training side. So today, let's talk about today. We're doing testing best practices. We'll talk about some equipment needed, tools needed. Cleaning and inspection will be really where we start. That's got to be the beginning of every good testing session. Installation, verification, and troubleshooting testing. What are the differences? What are the different equipment needed? Optical loss testing, OTDRs, and a few other tools we'll cover at the end that would be good to have in your tool bag. So, step one, all testing to begin with connector cleaning and inspection. Everybody who's involved in this industry will tell you the same thing. Why do we care? You know, there are a lot of people out there who bypass this. They say it's expensive. They say they don't have time. It takes too much time up front. But connector contamination or connector damage is still the leading root cause of failures in the field. We've seen studies. We've probably, many of us have seen the NTT study that was done years ago, and that may be a few years old now, but things have not changed all that much. When you talk to people who get out there with contractors and installers, they still talk about the most common thing they see is going out to the field, trying to troubleshoot something and finding that someone did not clean their connectors properly and they damaged the end face of their connectors, and you can't recover from that. That's costly in and of itself. The other thing we're seeing now with the higher speed networks is that the loss budgets are getting much tighter. Optical reflections are much more important than they were a few years ago when we were running in the megabit speeds, and now as we move from 1 gig to 10 gig to 40 gig, it's more important than ever to have nice, clean connections and low reflectance, particularly in single mode systems. So, again, you will save money and time if you clean and inspect properly. So it really came together for me when I saw this, when I looked up how big dust particles were and what really could contaminate your connector. When we talk single mode, we're talking about an 8 to 10 micron core. If you look at the size of an average dust particle, they run 5 to 10 microns, so it wouldn't take much to cover all or most of your core and block light coming through that connector. So, you know, this isn't just we're making a big deal out of small things. Small things have a big impact when you're talking about things that measure in microns. Bigger things can also get between two connectors and create damage, and that's irrecoverable at the end of the day. So we have rules on inspection. The IEC has a spec 61300-3-35. This is the most commonly used spec that focuses on different zones on the connector Endface and what needs to be clean, where there can be small scratches, where there can't, and all inspection equipment that has any automation to it can test against these and give you automatic pass or fail criteria. There are different settings for single mode and multi-mode fiber in the spec, so choose what works for your network. But if you're doing high-speed networks of any kind, large installations that might be on the edge relative to how much loss budget you have, you really need to make sure you have nice, clean connectors. Inspection equipment. So the most common thing we still see today is a handheld inspection scope. You can use it to check for connector damage. It's based on a judgment call. Someone's going to look at that and decide it's clean enough or it's not clean enough or it's damaged or it's not. So there's a little variability here. They usually can, they have universal connectors on them or they have interchangeable ports so that you can put different connectors into them. They tend to be lower cost than some of the automated equipment. We recommend 200 times magnification at a minimum. There are lots of scopes out there that go up to 400. That's even better. You'll get to see a lot more. Make sure it's an eye-safe scope. But at the end of the day, this is somebody deciding if that's going to pass or if it's going to fail. But this is certainly better than not inspecting at all. What we see growing a lot in the industry are these digital video inspection scopes. They display an image. They can do it on your iPhone or on your mobile phone or your tablet. They sometimes come with their own screen that you can connect to. Some of them are done with Wi-Fi. Some are Bluetooth. Some are directly connected to the display. There are a lot of options out there. Many of the scopes can connect to your OTDR and use the OTDR screen. So these are readily available. Scopes can have autofocus. They can be focused manually. And we're seeing a trend with larger companies that are contracting for installations or using their own people even, where they're requiring that a picture be taken of the Endface of all the connectors and included in the test reports when submitted. So you're not just having to test for loss or submit an OTDR trace anymore. You have to submit an image of your connectors to make sure they're clean. So again, not everybody's doing that. It's not everywhere, but we are seeing a trend that says that that's happening more and more often. Now, you've probably all seen this in one form or another. Dirty connectors, skin oils, dust, dirt from your bag, your tool bag, leaving it out, touching it with your fingers or palm can really damage or make the Endface dirty. And that truly affects the performance of that connector mating. You also have damage. Once it's damaged, it has to be replaced. So these are all, we don't make these up. I know we do them for display. We get them up on slides, but these really, we see these in the field more often than you might think. So we ran a little experiment. We took a couple of connectors that we knew were good. We put them in a tool bag in a carrying case and let them rummage around there for a little bit. And when we took them out, this was without their dust caps, we took them out, we took a look at them on the scope, and this is what they looked like. They had a lot of particulate stuck to them. So we put them together, and this will be a little bit of an eye chart for you, but we mated them, we measured the loss, and we got 0.9 dB loss, and then minus 37.7 reflection on that mated pair. So not a great connection, not something I'd want to put in my network. We took a fiber optic cleaner. In this case, we used one of the one-click cleaners. You can use one of the real cassettes. You can use a wipe or a stick, whatever you like to use, but we used a fiber optic cleaning product. We cleaned the Endface. We remeasured the same connection, and now we had 0.48 dB and a minus 56.7 return loss. So pretty typical spec might be 0.5 dB and a minus 55 or better return loss. So now that this pair would have no problem meeting that. Same connectors, simple cleaning. It doesn't take much to get these things to work right if you take care of them. So, and I know every time I do a presentation on cleaning and inspection, there's one or two skeptics in the audience who come up to me afterwards and tell me they never clean their connectors and they never have problems. And I would just say for every one of those people, there's probably 100 stories I can come up with that say if you don't clean, you can have problems. So I'm hoping that everybody looks at this as a very realistic possibility of damaging your network if you're not careful about it. So finally, wrapping up cleaning and inspection, use the right products when you clean. In the past, we cleaned to minimize damage more than anything. Now we clean to make sure that there are good loss results and good reflections as well. Very important in these high-speed networks. So use products that are designed for fiber optics. Find something that works for you, depending on if you're having to clean through an adapter because you have some installed base or you're cleaning patch cords or pre-connectorized cable assemblies. Pick what works for you. And take care using alcohol. You want pure alcohol if you use it at all. You're better off with a cleaner that is designed for fiber optics because they do leave a residue. You want to do a dry wipe after you do a wet clean if you have oils to remove because that residue will affect your reflections. So make sure that you follow up a wet clean with a dry wipe. All right, testing. Now that we've got nice clean connectors every time, what do we need to do for testing? And if we want to talk about best practices, we need to make sure first you have the right equipment for what you need to test. So you have to decide what the situation is. Are you inspecting a product that you've received prior to installing it, like testing a cable reel before you pull it in, or checking some patch cords that are delivered for your project? Are you doing installation verification? So you've already pulled in all your cable, you've connected your patch panels or whatever's in your network, and now you need to verify that you meet your losses. Or are you going out to troubleshoot? Because depending on what you're doing, you may need different tools in your tool bag. And then you need to consider what network you're testing. Is it point-to-point? Is it outside plant or inside plant? Is it PON, passive optical network, so it may be point to multi-point? Are you testing single mode or multi-mode? And then what do you need to report, whether it's for yourself, for a customer? Are they requiring loss only? Do you need return loss? Do you need to verify length? What are the requirements? And all those things will play into what equipment you need to put in your technician's hands to get the job done right. So the biggest difference between installation testing and troubleshooting testing tends to be troubleshooting teams will carry OTDRs. They need to. That's really the only way you can go find what's wrong with your network. Installation teams may have an OTDR, but always will have loss testing, so a light source and a power meter. So everybody needs to carry good cleaning and inspection tools. Installation testing needs to have a loss test set, some good reference cables for testing that. We'll talk about that in a minute. And if they need some documentation out in the field, they'll bring that. And then for troubleshooting, we'll add an OTDR with all the right connections. Most OTDRs have a power meter port, so you may not need a separate power meter if you have that. And we'll talk about OFIs, optical fiber identifiers, and visual fault locators at the end here. They're nice tools to have and can be very helpful. So testing, Tier 1 is optical loss testing, often fiber length as well, and polarity. Those are the key things that get tested in Tier 1 testing. Tier 2, we add an OTDR to that. And obviously, you need to match wavelengths. If you're doing dual wavelength testing, you need to make sure that your OTDR has that capability. And then you'll be checking, in Tier 2, you're checking for attenuation uniformity, loss, connectors, and splices, and what their losses are, and often testing for optical return loss as well. So for loss testing, you have a light source and a power meter. We'll use those to do a continuity check, because if you don't get light out the other end, you know something's broken. You can use them to check your transmit power level, your receive power level, and then they're always used to test end-to-end performance, loss from point A to point B. This is the most accurate way to test your network. This is the most accurate representation of the loss between 2 points. We'll talk about the equipment in a second, but you need a staff member at each end to do this testing. So there are a few different ways you can set up to do optical loss testing. Simply, the most simple way, you have a light source and a power meter. You have one tech at one end, one tech at the other, and you record that, and then you flip them and you test it from the other end, because we always recommend you test bidirectionally. So at a minimum, you need one set. Obviously, if you have two sets, then your guys can stay put, and they can test for loss in both directions without having to move. There are optical loss test sets that are set up with a light source and power meter integrated together, and they'll do bidirectional testing with one unit. And then there are more automated test sets, same basic idea, but more software. They handshake, and that really means that they know to change from 850 to 1300 nanometers for testing multimode, or if they're going to do 1310 and 1550 for single mode, they automatically detect that, adjust, and test in both directions with sort of one push of a button. So all the same testing. It depends on how fancy, how automated, how many features you need, and how much testing you're doing. Because obviously, as you go up in features, you go up in price as well. So that last version, the OLTS testers that are really automated are often known as certifiers. I'll just do one slide on this, but for anybody doing structured cabling, anybody looking to test to cover warranties, to document for warranty coverage or just for posterity, some of these certifiers can be very helpful, big time saving, but you're going to get these if you have a lot of things to test and document. They do bidirectional testing. Many of them now have automated test setups that walk you through how to reference your equipment, and with one button they'll sort of run through the whole testing scenario in both directions. So they're more costly, some of them. They're coming down as competition heats up, I think, here, but there are a lot of options out there from a lot of different vendors, and they can save you a lot of time if you're going to do a lot of testing. If you have to meet a certain, maybe you're testing to TIA 568C, you want automatic pass-fail, so you don't have to record everything and do your calculations or keep a long chart. These pieces of equipment will do auto pass-fail. They'll let you know they'll track if you tested and you failed, and then you maybe cleaned your connectors again and you passed. You'll see that history. So they give you a lot of great data. So that's, I wouldn't call this a best practice necessarily. It's not required, but this is something that can be very helpful in documentation and testing. So referencing, this, when we talk about best practices, this is one of the biggest things that we talk about. For those of you who've done any loss testing, the first thing you have to do before you test for optical loss is to reference your test set. I mean, and some of you may use the term zero out. So standards tell us that to measure the loss from point A to point B, we have three options in the standards. A test reference method, A, B, and C is how it's been referred to in the past. Now we talk about them as one jumper, two jumper, and three jumper reference methods. If we're going to focus on best practices, then we need to focus on the one jumper method. This is the best, most accurate, most repeatable way to test for loss. So it's quite simple, but most people do a two jumper and it's not nearly as accurate and repeatable. So for a one jumper method, you'll take your light source and your power meter. You have to start with them together in one place so you can reference them before you send somebody out to the far end. You take your test jumper, and a test jumper is a test reference cord. It's not some jumper that's been sitting in your tool bag for a year that you keep using. It's a test reference cord. It's been more tightly controlled. It has really tight tolerances on the ferrule and the fiber that's used in it. It's been interferometer checked to make sure the Endface is really good. And it will give you the most consistent launch into your network under test and most repeatable. So we highly recommend you invest in a few test reference cords for your testing if you want any kind of accuracy and repeatability. So you'll take your test reference cord. You'll see it referenced in some places as a TRC. So you take your TRC, you plug it into your light source, you plug it into your power meter, and on your power meter there'll be a button that says ref or reference or zero. You'll hit that and you will now see 0.00 dB on your power meter. Now you've zeroed it out and you've referenced it. You disconnect that test jumper from the power meter side, and only the power meter side. Never disconnect it from your light source. If you disconnect it from your light source, you'll need to start over again. So you disconnect it, and on your power meter side, you take a second test reference cord, and you plug it in to your power meter. Now you're ready to test. You plug each of these test reference cords, one into the head end, one into the other end, and now you can do your testing. This gives you the most accurate representation of the loss in that link. It allows you to see that last connector because you haven't referenced it out. So this is the one recommended by all manufacturers and people who do test equipment. Everybody you talk to will tell you the same thing. One jumper method is the most accurate. The other thing we need to talk about if we're talking about referencing and loss testing is in circle flux if you're a multimode user. So TIA 526 and IEC 61280, I think is the number, reference in circle flux as the most reliable, repeatable, restricted launch that you should have when you test for optical loss on multimode fiber. Today, most, if not, I won't say all, but most light sources, if you buy a new optical light source for testing, it will be in circle flux compliant to begin with. So you test everything as normal. It gives you the launch you need. It works fine. For those of us who have a lot of legacy loss light sources that we use for our testing, we may need to buy an EF mode controller launch cable. So it takes the older light sources. It manages the launch. It restricts the launch to the point where it's a really controlled spot size coming out of the cord and into your fiber under test. if we talk about best practices, encircled flux is the most repeatable, reliable best practice. Some people will not be happy that I even talk about a mandrel wrap because EF is really in the spec, but in all practicality, people don't always have an EF compliant source. They don't always have an EF launch cable. So a mandrel wrap may very well be your option to control your launch and at least make your testing as accurate and repeatable as possible. So the problem with mandrel wraps, for those of you who've used this before, and you probably know this, it's much more variable, so you're not getting as much consistency in your testing because it very much depends on the size of the mandrel, the type of material of the mandrel, how tightly you wind it, how many wraps, if you squeeze it after you wind it. So we see a lot more variability in that than we'd like, but it's better than not having anything. So if you're going to do that, here's what we would recommend. We have some sizes here for the diameter of the mandrel to use. We recommend 5 wraps around that mandrel, and so if your techs at least have a guideline, so they try to do the same thing and do it consistently. We don't recommend using a pen or your finger or whatever you find in your toolbox. It's nice to have something consistent and that won't overly strip modes out of that fiber. Now, the other thing to look out for with the mandrel wrap is if you have bend-insensitive fiber, this will do pretty much nothing for you because that fiber won't be susceptible to these wraps at all. So we don't recommend launch cables or any kind of test reference cords to be made out of bend-insensitive fiber. So a couple other just lingering things on loss testing. Something we see, people who do a lot of testing will often take their test reference cords and do a check on them every now and then by mating them together and keeping a log of that loss. It's a great practice to get into where you mate your reference cords, you look at the reading, they might be typically 0.2 to 0.3 dB, and you do that whether you do it daily or weekly as you test. At some point, you're going to mate those, and it's going to suddenly be 0.5, 0.6, maybe even worse. And that will tell you it's time to perhaps replace those cords. They're starting to get damaged. They're starting to get worn. Connectors only have so many matings in them, so at some point, you're going to get worse results in your testing because your test cords are going to get old or damaged. So it's a good practice to record that off and on, keep a little log in your tool bag, and make sure that they're not drifting out of control. During the workday, if you're doing a lot of testing, re-referencing your lost test set will help keep you on track as well. And again, keeping everything clean, keeping your work area clean as well will help protect everything. That's just a great practice to get into. And keeping dust caps on your patch cords when they're disconnected or anything that you're testing. Dust caps are there to protect from damage. They are not really there to protect from dust. They're really little plastic caps that have dust in them most of the time. So don't think that the dust cap is keeping your connectors super clean, but they certainly are protecting them, and they're certainly important. So make sure you don't lose them. Make sure you keep your connectors covered when not in use. OTDRs. Again, choosing the right equipment is key. There are a lot of things to consider when you choose an OTDR. You're going to use that piece of equipment to measure the length of your fiber, to check for breaks, to look at where your events are, events being connectors, bends, micro bends, splices. Most OTDRs will give you optical return loss values as well. So all these things are going to be done. You need to have the right OTDR for whatever you're testing. Some of them are used for monitoring. As you pull a cable in or you're doing splicing, there are different ways you can use it for live monitoring. And obviously, they have a lot of documentation capability to record information about your network and download for your reporting. So the key things to consider when you're looking for an OTDR is the dynamic range is important depending on what you're testing. Do you need a high dynamic range because you're testing really long distances, or you're testing higher loss networks because you do point to multi-point, so you have splitters or cascaded splitters where you're getting a lot of added loss and you need more dynamic range in your OTDR. The higher the dynamic range, the more you're going to pay for that OTDR. So it might be intuitive to say, let's just get as much dynamic range as we can, but you'll pay for that. So it may not always be warranted. Which wavelengths do you need? Do you need multimode 850 and 1300? Do you need single mode 1310 and 1550? Are you doing PON, so you need some other wavelengths? We'll talk about some of those, but it's important to buy what you need to cover all the testing needs. And just what do you like? Do you want it small and portable? How easy is it to use? The picture at the top is a tiny little OTDR that almost fits in your pocket. The lower one is bigger, kind of tablet-sized. There are modular and dedicated OTDRs. The modular ones tend to be a little bit bigger in some cases, but you can swap out modules and do different types of testing with the same fundamental platform, so that might be something good for what you need. You may not need that. And then what other features? What do you want to pay for at the end of the day? So once you decide all of that, the other thing you're faced with today is with these new icon graphic views, whatever you want to call them. There's something that we're seeing a lot of in the field and a lot of interesting feedback. We thought this would be something that people would really pick up on. Icons are so much easier. They're red if they fail, they're green if they're good, they give you data, they might give you helpful hints on what could be happening. So these are very helpful. But the feedback we get from field techs and from some of the supervisory personnel is that they really still want their techs to understand what an OTDR trace is about, what it shows you, what you can learn from your network by evaluating an OTDR trace. And when you're troubleshooting, sometimes it's better to look at that than some icons. So although this is very helpful for lower skilled techs and for getting some quick answers, it's not always the end-all be-all for everything you need. So as you're considering what to buy or what to use, think about the big picture. The icons are great and they can be very helpful, but they may not be the entire solution. So I thought it would be good to go over just a few things that the OTDR traces or the signatures can tell you, and it's important to make sure that your techs or your personnel using them understand. So one of the main things that you'll see in an OTDR signature is a non-reflective event. These are indicative of a splice or a splitter or a bend of some kind. It's light being lost due to something abnormal happening along the length of the fiber. We also see reflective events, and the OTDR will pick that up, and it looks like a spike. Those are connectors or mechanical splices or a break or the end of the fiber will have a reflective event. Reflections occur because of an air gap of some kind. So it can tell you a lot about what might be happening in your network, especially if you weren't planning on having something at that particular position. Something's wrong. The other thing we see a lot, and it really confuses people, is what we call a gainer. When you see an optical gain in a trace, there's something going on in the core variation, or a couple of fibers maybe spliced together that are a bit mismatched. And you deal with this by doing bidirectional testing, which is a best practice anyway, even for OTDRs. We recommend you test in both directions and you average your losses at every event. In this case, if you test from the other end, you'd see a loss and you'd average those two numbers. It's highly likely that there's something spliced in between position 2 and 3 here, 2 being a loss in this direction and 3 being a gain. And when you test it the other way, it would be number 2 would be the gainer and number 3 would be the loss. You'd average those and your network's really fine, but it can be a little bit confounding. One of the key things that people who do OTDR testing really need to understand is setting the right index of refraction. The index of refraction is provided to you by the fiber manufacturer, and anybody going out to do some testing should have that value. If you get it wrong, if what you enter into your OTDR doesn't match the actual fiber, your length calculations will be off. That may or may not be the end of the world for what you're testing, but if you look at these numbers, just to show you how it doesn't take much to have the length be off. In the example here, 1.471, if that's what the index of refraction should be, and you're off by 1/1000th, you'll be off 7 meters in a 10-kilometer span. That's not so bad. If you're looking for a splice and you get within 7 meters of it, you can probably find where that is. In the case of the second line where you're off by 1/100th, which still isn't a big number, you can be 66 meters off in a 10-kilometer length. So, and now a little bit harder to pinpoint a problem, and so on. So it's an important value to know and to keep with you and to use for your OTDR setup. Pulse width is the other item that we get a lot of questions about. If you're trained and knowledgeable on OTDR testing, then you'll understand how to set your pulse width to get the best trace you can and the most accurate results. In general, a shorter link can use a shorter pulse width. The pulse width is basically how long of a light pulse you send into the fiber for the OTDR to use to calculate the distances and the losses. So longer pulse widths allow you to reach much longer distances, but if you have a short link and use a short pulse width, you'll see events that are more closely spaced together. You'll get more visibility, but you won't reach out as clearly to longer lengths of fiber. So you have to find a balance between those two. And we recommend that you use the shortest pulse width that provides a nice clean trace. And this is where training and understanding of OTDRs really comes in. We encourage anybody who's going to do OTDR testing to really get a spool of fiber or a length of cable and do some experimenting on your own, because the best way to figure this out is to kind of see the results as you make changes. Change the pulse width and test the length, and then change it again and test it again, and take a look at that trace. Is it nice and clean, or is it really noisy? Are you seeing things clearly? Are you able to see a connector? Are you able to see the end? And it'll start to really click with you what works and what doesn't. So relative to testing, if you're testing for fiber to the home, fiber to the building, any kind of PON network, I just want to do a quick check here, since a lot of people are moving into that space. We get questions about, do I need different things if I'm starting to work with fiber to the home? So relative to testing, the different challenges you'll see with PON networks is you may have added wavelengths that you have to deal with. So 1310 and 1550 are the traditional testing wavelengths for single mode. You may have to add something at 1490 if you're doing FTTx testing. You may be requested to do out-of-band testing at 1625 or 1650 nanometers. So those are things you might have to look at. Do you have enough dynamic range to get through optical splitters? PON networks are point to multi-point. If you add splitters, 1x4, 1x8, or a couple cascaded splitters, you're adding a lot of loss at those points, and you may need something with better dynamic range. Just adding in a 1x8 splitter will give you an extra 10 dB or so of loss in that link. So suddenly you may have trouble if your OTDR does not have a particularly high dynamic range. So you have to consider those things, right? You may also need to train your technicians a little bit differently if they're faced with these and they haven't done them before, just to take a look at what splitters look like on an OTDR trace. and just to understand the differences. So common OTDR issues. So the dead zone is something you really have to deal with, and some OTDRs deal with it better than others. So first, the best practice in testing with an OTDR is to use some type of launch cable, launch box, fiber ring. There are a lot of different terms used for it, but it's a spool of fiber that's anywhere from, I guess the shortest ones tend to be about 100 meters up to 1 kilometer, and you use that to launch into your cable under test. And what it does is it gives you it gives the OTDR some time to settle down after the launch, and allows you to take a look at the very beginning of that link, the very first connection, the very first patch panel, if that's what you're going through. And it allows the OTDR to see that and report that accurately. Without a launch cable of some kind, you're going to lose everything that happens in the first few 10, maybe up to 30, 40, 50 meters. You won't see that in your OTDR. It gets lost in the noise. So you want to test with a launch cable. Again, shorter pulse widths will give you shorter dead zones. OTDRs tend to have a problem when when there are connectors closely spaced. So if you think about a central office or an equipment room or a data center and all the patch panels and interconnects that can happen in that environment, I think the most common patch cord sold today is something like a 3-meter or a 5-meter patch cord. So if you've got some interconnects where you've got a couple of patching units close together and you run from connector to connector and you've got 3 meters between them, or you've got a splice and patch panel where you splice in and you have a meter and you go to a connector, it's going to be almost impossible for an OTDR to see those events as separate events when they're that close. It's going to see it as one event. Some OTDRs are better at kind of parsing through that and reporting closely spaced events, but it's not always something that you can look at. So the more you can adjust your pulse width to be shorter, the more you can make sure you launch into some kind of launch cable to settle your OTDR trace down to be able to see those, the better you'll be. But closely spaced events are one of the most difficult things to deal with in the OTDR measurement world. So you may know that there's something going on with high loss in a patch panel, but if there's a couple connections close together, you may not know which one's really giving you the trouble. So back to the OTDR issues, connector mismatch. Believe it or not, we see APCs mated with UPC. For those of you not so familiar with the technology, APC is angled physical contact and UPC is ultra-physical contact, which is a flat face or flatter face. APC has an 8-degree angle, so if you try to mate those two connectors together, you're going to have both damage and loss. We try to make that harder. APC connectors are green in color. UPC tend to be blue or tan. So it should be a visual sign if you see two different connectors not to mate them together. Receive fibers. Again, in best practices, we recommend that the other end of your link, the far end that you're testing with an OTDR, has a receive cable on it. Now, we understand that's not always possible. When you're troubleshooting, when you're out there looking for something, you may not be able to go to the other end. But in the case of wanting to get a really accurate measurement, to really look at the very end of that link, you'll get the best results by putting a receive cable on the end of that so that you can test that very last connector. Gainers we talked about, they're just variations in the core or the fiber segments, and using bidirectional testing will help you average that out and get rid of that problem. And then your lengths. If you're really trying to get an accurate length, you really need to make sure that index of refraction is correct. Otherwise, you're gonna be off by possibly tens of meters. And also remember that fiber length and cable length are different. You're measuring the fiber. In many cable designs, particularly higher fiber count, loose tube outdoor cables, those cables are stranded, so there's more fiber in that cable than there is cable. So you have to adjust for that as well. If you see a break in your fiber and it's 12,252 meters away from where you're standing, you're going to have to adjust the fiber length for the cable length, and it won't be quite that far away in the cable because there's more fiber than there is cable. So those are things that technicians should know about. A lot of the manufacturers of the test equipment can help you with those calculations. We can certainly help you with those calculations, but don't mistake fiber and cable length for being identical. So in summary, we talked about launch cable, receive cable. Those are two important things to get accurate results. Clean your connectors, clean your test cables so you don't transfer bad dirt and damage onto whatever you're testing. Make sure you test all wavelengths that are going to be used, particularly in single mode. Well, it happens in multimode too, but in single mode, 1550 nanometers is much more sensitive to bends than 1310 nanometers is in standard single mode. So passing at 1310 does not mean you won't see a problem at 1550. So make sure to test all wavelengths that are going to be used in this network. Test from both ends and do bidirectional averaging for loss testing and OTDRs. Make sure you have the right equipment, set your equipment up properly, and keep it all clean and well maintained. So last piece of equipment we'll talk about. A couple other things to have in your tool bag, particularly if you're doing troubleshooting, but we find at least the VFL, the Visual Fault Locator, to be something that everybody should have. And most OTDRs will have one built in. Fiber identifiers are a piece of equipment that you can attach to a cable to one of the jumpers on one end and find out if you have live fiber. So before you're going to disconnect it, it's a great thing to check. It's a really important one for troubleshooting teams. If you're doing fiber to the home and you've got a 1x8 splitter and you're trying to figure out which leg is not active, it's a really great tool. You have to be careful if you have bend insensitive fiber. Many of these identifiers will not detect light in a bend insensitive fiber. They work by pinching the fiber just enough to leak out some light and see that it's live. Bend insensitive fiber just won't leak light that way. So there are a couple in the market that work well. There's one in particular that's designed for bend insensitive fiber. We found to work well, but don't be fooled that you don't have a live fiber if it might be bend insensitive. So that's a good tool to put in the tool bag. Visual fault locators, VFLs. They're some people just call them red lasers. They're great for troubleshooting within your patch panel where your OTDR might not be able to distinguish exactly where something is. It can't get that precise. You can shoot the red laser into that end, and if something's broken or even cracked or damaged in any way, you'll see some red light leak out, and you can find that damage. So that's a really handy tool, not particularly expensive, so great to have in the tool bag. And then you may need talk sets, depending on what people use for phones or what other equipment you have. But especially when you're doing loss testing and you've got somebody on each end, you want to be able to communicate. And on the fiber identifiers, beware of dark cable jackets or dark colors. If you've got a tight buffered fiber that's the dark blue or black, those are a little bit harder to detect for some of these fiber identifiers. So when you have yellow jacket cable or you have white fiber, if you're doing 900 micron or lighter colors, you're fine, but some of the darker colors can be a little bit difficult. So in summary, we know testing is a critical part of maintaining your fiber network, and today's speeds, we're going up to a lot of networks needing to work for 10 gig, 40 gigabit, 100 gigabit and up. things are not as forgiving as they used to be. Used to have a lot of extra loss in your loss budget. We used to see a lot of networks that needed attenuators on one end because there was just too much light getting to the receiver. Those days have kind of come and gone at this point, and everything needs to work just right to be able to move to the next level. So these things are really important. Bad habits, taking shortcuts, we see it all the time in the field. It's a good time to go back and look at your procedures and make sure you're doing things right. Clean those connectors. Don't let the little things add up to big problems later. And make sure you have the right equipment. Don't hesitate to, if you need a new OTDR or some new test equipment, call different manufacturers. Ask about what you're doing, what they would recommend. See if you can get demos of some things, particularly if you're going to go out and buy a few different pieces of equipment. Invest wisely. So take a look around. There's a lot of great equipment out there. There's a lot of great vendors, but there are certain things that you need for what you're going to do. So take some time to look at that. And accuracy and repeatability really do matter in these networks. So good procedures that are followed regularly are really important. So we're going to enter the question and answer period. I'll take a look at the questions in a second. If we don't get to your question, we will try to email everybody who submitted a question and get them answered in the next day or so. If you think of something after this webinar is done and you want to send us an email asking us later, feel free to send something to our tech support line at support@lightbrigade.com. Give us a call or just contact me directly at lee@lightbrigade.com. So we'd love to hear from you. So let's take a quick look at some of these. So we have one question is, why isn't there a standard for testing patch cords? I don't know what you mean by a standard. So the manufacturers of patch cords do have standards that they use when testing their patch cords before shipping. They test for loss of those connectors. They usually do some interferometer testing to take a look at the Endface and make sure it meets the Telcordia requirements. So depending on the manufacturer, they can have a whole slew of tests that they would provide to assure that those patch cords are the quality that you want and the loss that are able to achieve the loss that you want. If you're referring to test reference cords, it might be a little different, but there is a standard for testing patch cords. What does a receive cable look like? Is it just a connected fiber jumper at the end? It's actually, for OTDR testing, a receive cable should be similar to your launch cable. So it could be a fiber ring that's 100 meters or 150 meters connected to the other end, so you can clearly see where that last connection is, and then you should see that other length of fiber. So it needs to be long enough so that it doesn't get lost in the noise and you can really detect that last connector. So we'd recommend something like 100 or 150 meters, just so you can assure that what you're looking at the very end is that last piece of cable. So the next question is, OTDRs are primarily used to measure insertion loss, return loss for longer cables. Are they effective for short cables? What does that say, Gina? Short cables of 60, 1 foot as breakout cassettes, or should some other tool be used? So I think the question is, can you use an OTDR to look at a cassette? So the cassette, for most OTDRs, a cassette that's got like a 1 foot or a 1 meter length of cable between the back end and the front end will look like one event. So, so if you don't have a problem in that cassette, then using an OTDR to test through that, it will show a loss. It will be a combination of whether it's a splice or two connectors in that cassette. It will show that as a loss. So if you're in spec, then it's no problem to use the OTDR to test that. If that is reported as an out of spec and that's where your cassette is, Then to really troubleshoot it, you're probably going to go in with a visual fault locator and through one of those connectors and try to see where the problem is. So, so you can use it. It's just not going to give you a precise location within that if it's a splice or if it's two connectors, which connector it is, because they're just too close together. All right, we have about 4 minutes left. Let me get a couple more questions. So what type of source would you use for multimode testing? Is a VCSEL okay to use? Yes, a VCSEL is okay to use, and LED is okay to use. Just make sure, if you want accurate results, that it's an EF compliant source, encircled flux compliant. If not, use your launch cord, your test reference cord with a mandrel, so that you have a nice restricted, repeatable launch. So there's a question on single mode loss testing for one jumper method. How is the loss of the test reference cord number 2 obtained since it's not included in referencing? Or is test reference cord number 2 considered minimal and therefore omitted? So yes, the second part of that. So the test reference cord is going to be a short cord, maybe a meter. So the fiber itself has negligible loss. And what it's doing is it's allowing you to test the loss of that last connector in your link by mating to it. So if you reference that out, like they do in a 2-jumper method where you reference out both test cords, you would not account for that last connector in your network. So you would be measuring lower than what the real loss is, because you would be referencing out one of your connections. So unless you're using really long test reference cords, which we don't recommend, that 1 meter of cable is insignificant in your test. Do you use the same tools to clean UPC and APC connectors, or are the tools different? They're the same tools. There are one-click cleaners, and the cassette, you can clean on the cassettes. The one-clicks, you buy the APC type so that it angles properly. The wipes and everything else work the same way. So the key with APC connectors, being angle polish, if that's specified, then you know that that network is really concerned with reflections. So just really make sure you do clean. Most products will tell you what they can be used for, so just pick a part number or a style that says works on APC connectors. But they all basically look alike. All right, we answered the index of refraction. Is that the length for the cable or the fiber? As I said, that's the fiber length, and you're going to have to adjust for the cable length depending on the kind of cable you have and how long this is. So again, we can help you with that. Manufacturers of your test equipment can help you with that as well. And a lot of cable manufacturers can help you answer that question as well. All right, so here's a question. If attenuation fails a threshold setting, but the system passes the OLTS power test, OLTS being optical loss test set, would the attenuation still be considered an issue that would need to be resolved? Attenuation fails a threshold setting. So I guess for that one, I may contact you to get a little more information. I'm not sure the threshold setting is set by you or a spec, so I'm not sure how you'd fail one and pass the other. So we'll try to contact you about that one. Is there a standard for recommended pulse width setting for OTDR testing? Again, it really depends on the network and the length. We can provide you with sort of some guidance, but at the end of the day, there are a lot of variables that come into play. The shorter the length, the shorter the pulse width. So if you use that general rule of thumb, you can get some you'll get some good results. All right, I think we are at our time. I want to thank everybody for coming. We will get, as I said, we'll try to answer any of the other questions by email. Sorry we couldn't get to everything. Appreciate your attention and your time today. We have an upcoming webinar on December 1st. It's going to be why is fiber characterization important in today's networks? And we hope to see you or any of your colleagues at that. Thanks, and have a great day.